All right, this is going to ask us to analyze the motion of this graph. They tell us that this represents a car and that the car starts at position. I'm going to write this x equals 0. So I'm going to write x sub 0 equals 0 meters. Whoops, there it is, that you can see it a bit better. It tells you that in the very top there. And it says that the velocity versus time graph is over here on the right. So the very first thing they want you to do is to take the equation for a line. So y equals mx plus b, and they want us to rewrite it to create an equation specific to this case. So how you do these, kind of like we practiced before, is the y-axis becomes v, velocity, because that's what it stands for. They tell you that they actually want you to put a number for the slope, so we can look at this, that the slope is the rise over the run, so we drop 4 over 1, so the slope you can see here is -4. So -4 meters per second squared would be the slope, because it would be meters per second over seconds. Or you can just think the slope is the acceleration, so that's going to be the value. The x-axis here represents the time, so we'll multiply that slope times the time. And the b value here is the y-intercept, which is 12. So the initial value was 12 meters per second. So we've created an equation based upon this graph that the velocity at any given time can be predicted by plugging into this equation. You would take that time, multiply by -4, and add 12 to it. So for example, let's just check it for 2. Put 2 in here. 2 times -4 is -8, plus 12 is 4, so it does. It works. It gives you the value of 4 there. Or 3 seconds. 3 times -4 is -12, plus 12 is 0, so the equation works. And then they just say, what does the slope represent? We already know this. The slope represents the acceleration of the car there. Since a velocity versus time graph, the slope's always acceleration. So then they want us to fill in this little chart here. So I've got it right here. And it says, Carlos says, the car is slowing down for the entire distance it travels because the slope of the line is always negative and never changes. So you have to sort of refute Carlos here that the car is always slowing down, which a lot of people would want to say. So here's what we think. The car starts with an initial velocity, and we've already said that, but let me bring this back for a second, of 12 meters per second. And initially, it is slowing down. How do we know it's initially slowing down? Because we are approaching the x-axis, which represents 0 meters per second. So it starts with 12 and is slowing down for the number for the first 3 seconds, and then it is speeding up for the last second. How do I know it's speeding up for the last second? Because that's from 3 to 4, we're moving away from the x-axis. We went from 0 meters per second to -4 meters per second. At 3 seconds, the car motion changes from traveling. So at 3 seconds right here, we were traveling in the positive direction. How do I know that? Because I was above the x-axis. Everything up here is a positive velocity. So we're going to change from going in the positive direction to being down here and going in the negative direction. So at 3 seconds, the car motion changes from traveling in the positive direction here, I'll circle, to traveling in the negative direction. The horizontal intercept, so that is right here. That's the horizontal intercept. So what is that going to represent? Well, it represents the time at which we're at 0 meters per second. So the horizontal intercept represents the time when the speed, or velocity you could write, would be a bit more accurate actually, of the car is equal to 0 meters per second. The car accelerates constantly with we already figured this out, magnitude of -4 meters per second, and I actually forgot to add a line here, and that's because right here we should say slope of the line never changes there. It is a constant slope, so it's a constant acceleration. All right, last part here really quickly is they ask you to make 2 more graphs. So the first one is an acceleration versus time graph. Well, that's pretty easy. We've already said the slope is constant the whole time. It's -4 meters per second squared the whole time. And your acceleration versus time graphs, with few exceptions, will always just be straight lines there. So that's it for the acceleration versus time. The position versus time is a lot harder. Okay, so they sort of help you out here and they give you a dot here. And let's talk about how they know that. First off, this one's easier to know because they say you start at 0 meters at time 0. So you know that that dot's there. So how did they figure this dot out? Well, let's come back to this for 1 second. And remember, we mentioned on one of these days that the area under the curve, so to speak, of this represents a change in position. So I could figure out that area, because it's a triangle shape, by 1/2 base times height. So 1/2, my base is 3 seconds. My height is 12 meters per second. So if I multiply that out, I'll do it in slightly. That's 36, and half of 36 is 18 meters. So we've changed 18 meters in that first section there up to 3 seconds there. And if you wanted to do it for here, you could actually also get it for this little part right there. In that part, also 1/2 base times height, but this time the base is 1 and then the height is 4, so it's going to be 2 meters. That's negative area because it's below the x-axis, so it's actually going to be a change of -2 meters. Remember, both of these don't represent necessarily where you are, they represent changes of your position. But since we started at 0 and our change for this first triangle is 18, we're going to wind up at 18. And then after that, this is 12. Each one of these are divisions of 6 here, so 3, 6. We're going to drop 2, so we'll be somewhere right about here. We'll drop 2 more by the end. Last thing we need to think about here real quick is what is the shape of this graph? Well, we're accelerating, so we're going to have a curved graph. We have a negative acceleration, so we're going to have a negative curve, a frowny face on our graph. And then one more way you can think about it is, besides it being a frowny face, is we've got to be slowing down. We've already said that. So let's see, I'm not going to be able to draw this great by hand. We've got to reach 0 by there and then start to, come back down there. There you go. So that is the basic shape of the graph there. A negative acceleration will produce a negative curve and a frowny face.